What is CF?
All right. Again, good morning, everybody. Let's start. Last time we went through a derivation of an adiabatic process, and we got the relationship between the pressure and the volume, right, in an adiabatic process. So we're going to do an example, but before then, if the process is adiabatic, we defined something called gamma, right? And it was the Cp over Cv. And if the gas is monatomic, versus diatomic, for monatomic, it's I think it's 5/3, and for diatomic, gamma is 7/5. Let me just double check to make sure. 5/3 is about 1.67. Yeah, that sounds right. Yeah, good. Yeah, 5/2. Okay, so that's gamma, and we got the following relationship that P1 V1 to the gamma is a constant, or PV to the gamma is constant. So P1 V1 to the gamma is the same as P2 V2 to the gamma, right? So, okay. So here's an example. Suppose you have a gas here, and it's diatomic. Okay? Let's say it's diatomic. And you're given the pressure at the beginning. It's 1 atmosphere, and then the volume is 500 cubic centimeters, and then the temperature is 30 degrees Celsius, and 30 degrees Celsius, immediately add 273 to it. So 30 degrees, 303, is that right? Thank you. So what you do is you compress this gas adiabatic. And so that means feel free to use this equation. So you compress it and until the volume here becomes 1/10 of what it was. It becomes 50 cubic centimeters. So the question is, what is the pressure? What's the temperature? And then how much work is done? Okay. If I say how much heat is put here in this process, how much heat was added or taken away?
No heat. No heat.
No heat, because?
Adiabatic.
Yes, good. Yeah, by definition, good. So how are we going to do this? I think a good starting point could be here. That would be a good starting point. So you would say P1 V1 to the gamma is equal to P2 V2 to the gamma, and so P2 is equal to P1 V1 to the gamma over V2 to the gamma is the same as V1 over V2, the whole thing to the gamma. So V1 over V2, the whole thing to the gamma, right? Yeah, that's good. So what is P2? So P2, P1 is 1 atmosphere. I can leave it as 1 atmosphere for now. And then V1 over V2. Should I convert to cubic meters? Or because I'm taking the ratio, the cubic centimeters cancels? It doesn't matter. So good, yeah. So V1 is 500. V2 is 50. Again, I didn't bother converting because I'm just dividing them, and the units will cancel anyways. And then gamma is 1.4, right? Because 7 over 5 is 14 over 10, which is 1.4. So 1.4. So if you do this, you will get, well actually, why don't you do this? I'll give you a moment to do that.
ATM is Pascal as well.
So we'll get ATM and then we'll change it to Pascal, yeah,
Oh,
yeah. So let's do that.
One point four?
Yeah.
One foot
So 10 to the 1.4 power, right?
25.19.
25.19, thank you. So it's 25.2
Yeah.
atmospheres. And you can multiply this by 1.013 times 10 to the fifth to get the Pascals.
25.45.
oh,
Pascals or kilopascal?
I got 2,544,540.
And that is.
Yeah.
Okay, so it would be 2.5 times 10 to what power?
Oh, to the.
Six?
Sixth.
6,000. Alright. About, okay, I'm rounding, probably not. By the way, in a quiz or something, if you want to, always assume it's 4 significant figures, even if I don't write them. So, don't round to like 1 significant figure, definitely not, or just 2. I prefer just keep 4 at all times if you're not sure. Like in the quiz, we had one question. You ended up with 17 over 25. That's fine with me. If you don't have a calculator, leave it at 17 over 25. Yeah. Okay. So that's the pressure. How am I going to get the temperature, T2? Yeah, PT equals to nRT, the ideal gas law. And so you have P1 V1 over T1 equals to P2 V2 over T2, right? Use the ideal gas law. Relate the 2 states together. So you get what? P1 V1 over T1 equals to P2 V2 over T2, right? And I'm looking for T2, so that means T2 is equal to what? P2 over P1, and then V2 over V1 times T1. Does this sound right? Cross multiply and then divide? Yeah, the P1 and the V1 will be on top. Good. So now, T2 is equal to, and the reason I didn't really care much for changing the units is, you see, you get P2 over P1. Again, if you leave them in atmospheres, they're going to cancel anyways. So this one is like 25.2 atmospheres over 1 atmosphere. So that cancels. And then V2 over V1, V2 is 50, and it used to be 500. So the cubic centimeters, again, they cancel. And then the temperature T1 is 303. And so you get 761 about 760 something. Okay. And if you want degrees Celsius, it's about 488. Pretty hot, right? 488, yeah. It used to be 30. 30 is a little bit warmer than here. Good. So now, how much work was done? What would be the
W equals Q plus.
PdV? I can integrate PdV. The problem is I have to integrate something to the gamma.
Oh.
But we could, but it's easier to do it another way.
N times CV or CP times something?
Okay, so you're saying this. I know that the change in the thermal energy is Q plus W, or W plus Q, but this is 0. So if I find the change in thermal energy, I can find W. Change in thermal energy is N CV delta T, right? That's the change in thermal energy. Okay. Now how much is N? Well, you can use PV equal to nRT to find what N is. So it would be P1 V1 over RT1. right? The number of moles. So let's write it down. So W is the same as delta E thermal, which is equal to N, but N is P1 over R P1, right? What is CV for the atomic gas? 5 halves, right? 5 halves, 5 halves R. It's somewhere in the notes. If you don't remember it, it will be provided for you. Just now. And then delta T is the T2 minus T1. So the change in temperature. So 761 minus 303. Well, the R goes away. This R cancels. And plug in the numbers. So now you have to, you see, the P, there is nobody else to cancel the atmospheres, right? We're not taking ratios. So we need to be in Pascal, thank you. And then V, we need to be in cubic meters. So to go from cubic centimeters to cubic meters, you have to divide by a million. And then for the pascals here, times 1.01 times 10 to the 5th. Yeah. So let's do that. According to my calculation, I have, well, I would say it would.
Why did you put 5 halves?
5 halves. That is CV for a diatomic gas. 5 halves are.
Oh, that diatomic was. Oh, that's
gamma.
That's gamma.
Yeah.
I've got 76 versus 2.
76. Okay. I would wait for another answer. Yeah.
It's not another answer, but why is heat 0?
Because it's adiabatic. Yeah.
Thank you.
Yeah.
Is it 191 joules?
I got 191.
Not it.
Yeah, it's you have to plug in. Yeah.
What's the answer?
Oh yeah, let's write it down. It's about 191. 192 maybe. So, continue?
So the temperature changes, but the heat is 0?
Yeah.
Can you explain that real quick?
Yeah, so there are different ways to change the thermal energy. Is by, you can do work on it. That changes the thermal energy, which means the temperature will also change, even if no heat is added. Heat is just an energy transfer from higher temperature to lower temperature. But to change the temperature itself, you can add heat or take away heat, or you can also do work. Yeah. Yeah, it's they're related, but they're not the same. It's kind of confusing at the beginning. Heat, temperature, they should be the same, but they're not. Yeah. So, well, speaking of heat, we add heat, take away heat, but how do we do that? Basically 3 processes, which gets us to this heat transfer mechanisms. You got, does anybody remember them from way back when?
Radiation,
And so you mentioned it, the third one.
Conduction?
Convection, yeah.
Okay.
Yeah,
Convection.
convection.
Yeah, that's.
So conduction, well, it conducts. And we all learned it probably when we were kids, painfully. You got something hot and it goes from the heat transfers from the hot to your body, which is usually, typically 37 degrees. So something is boiling, it hurts. So you can do that by conduction. And conduction usually by a rigid object. Convection is by a fluid. A fluid can move. The actual fluid that's hot in here, this piece of the fluid can go there and then gets replaced by another fluid that's a little bit cooler, and it just circles around. That's the convection. We have two formulas, and then the other one was radiation. Radiation is the electromagnetic radiation from, let's say, light. Huh? Any radiation, yeah, it's all radiation. It can be visible or, huh? Yeah, so we're going to, we have two formulas. One of them is one for conduction. Convection is just qualitative, we just mentioned it. And then radiation. We have another formula for that.
Did you go over convection?
Yeah, convection is when a fluid just circulates. So let's say you're in the room. Let's say it gets hot at this spot, right? I have a heater. I turn on a heater and it heats the air here. When the air gets hot, it becomes less dense, right?
Yeah.
If it's less dense, it will rise due to buoyancy. And then if it rises, it doesn't stay vacuum here, right? It gets replaced by another part of the air in the room. And now this hot air goes there, it heats the whatever is adjacent to it. And then the cool air that used to be cool replaces this one, now will get hotter, and then it keeps circulating.
Okay.
Yeah, so for convection, the actual thing moves. But for conduction, if I have a rod, let's say this is the stove, I place it here. Let's say this is iron, right? I place it at the stove here, at the hot plate. Let's say it's 200 degrees. And I touch it from here, heat will flow from here to here. But it doesn't mean that this part of the rod physically moved and came here. Just the heat transfers through it. Okay. So let's do conduction and then radiation. So conduction. So let's say this here is a rod. This is hot. This side is hot, and this side is cold. Heat cold, right? This is the hot side. This is the cold side. So heat will flow from where to where? From hot to cold. Okay. So now it will flow at a certain rate, right? You will get a certain number of joules per second, right? So the question is, how many joules per second am I getting? That's dq dt. dq dt will be in joules per second, right? And a joule per second is called a watt, right? It's power. It's power. A joule per second is a watt. 1 watt. W watt. Okay. So what would this depend on? Let's say somebody who's here versus way over there. Do they get the same amount of energy per second? No. So the farther away you get less, right? It transfers slower. So it would probably be inversely proportional to the length, right? So the longer it is, the worse. So it's inversely proportional to the length. How about a wide rod versus a really thin one? Which one would transfer more heat?
The thin one.
The really thin one would transfer more?
No, the wide one.
The wide one, yeah. Because if I put, let's say I have a thin one,
Oh.
yeah. Let's say the thin one transfers 1 joule per second. How about if I get two thin ones and each of them transfers 1 joule per second? So I get 2 joules per second. Each of them will transfer. So it has to be proportional to the area.
So would the thinner one transfer faster?
The thinner, no, because it has less area. If it's the same length, less area will transfer slower. Yeah. And then how about if the temperature difference, let's say, if it's just 1 degree versus 200 degrees, heat will flow faster or slower if the difference in temperature is large? If it's large, yeah. I mean, first of all, if there is no difference in temperature, you won't have the heat transfer. And so the more the difference, so it's proportional to the change, to the difference in temperature. Okay? Difference in temperature. And now, what about a copper rod versus a wooden stick, which one will transfer more?
Copper.
Copper. So there has to be something that depends on the material, that is K here. It's the thermal conductivity of that material. Now the thermal conductivity, you get it from, it gets measured and it's called K, and you get it from a table, alright? And I will give you, well, the table is there, I can't write the whole thing, but I will read some numbers out. So again, K is the thermal conductivity. A is the what? Cross-sectional area of the material. Let me just write area. L is what? Length. And delta T is the difference in temperature. Yeah, and then this K, I mean, the left side you have joules per second. So K has to somehow make it joules per second. So area over length will be in meters, right? SI units will be in meters. So I need to cancel meters. So I have K must have 1 over meters. And then it must have 1 over degrees Celsius or Kelvin. Same thing, right? Because it's different. And then you must have joules per second. Units. So the units for it are watts per meter per Kelvin or per degree Celsius. So here are some examples. For example, let's see. Silver is a good heat conductor, or copper, 400. K is 400 for copper. For aluminum, it's about 240. For iron, it's 80. For let's see, concrete. Is concrete a good conductor? No. Yeah. So it's about 0.8. And then glass, it's about 0.8. Styrofoam is not a good conductor of heat, right? It's good for insulating, right? And so it's 0.035. Yeah. And air is like 0.023. Also a poor conductor. It's a good insulator. Poor conductor is a good insulator. All right. So just a quick example. Let's say I have a copper rod. So here is. So this is copper. And let's say the length is L equal to 1 meter. Right? L is equal to 1 meter. And let's say the temperature here is T equal to 200 degrees Celsius. And the temperature here is T equal to 0 degrees Celsius. So this is the cold, and this is the hot. Let's say dq dt, it's transferring 100 joules per second. So let's say dq dt is 100 joules every second. Well, what do you think the question will be?
What's the height? What's the area?
What's I think yeah. What's the area? I think by height you mean radius of this thing. So yeah, basically, what is the radius? If it's a circle, right? It's a cylindrical wire. So find what is hot. Plug in. So let's plug in. You got dq dt is K for copper. We'll write down what K is for copper. The cross-sectional area is pi r squared, right? And then delta T is delta T, T cold or T hot minus T cold. Just write delta T for now, and then L. So the left side you have 100. What is K for copper? Oh, you go to a table. Yeah, don't memorize it. Yeah, never do that. Yeah. So 400. Yeah. 400. And then pi, and then r squared delta T, it's the
200.
200, yeah, 200 minus 0 is 200. And then the length is 1. So solve for R. So R is 0.02 approximately. Meters, so that's 2 centimeters. So the radius of this thing is 2 centimeters. But, so it's about 2 inches in diameter, a little bit less.
4 inches, right? In diameter.
2 centimeters is slightly less than an inch.
Oh, amazing.
Okay, so, yeah,
Going back, can you explain why the thin rod doesn't heat up as fast as the larger rod?
oh, it doesn't, it doesn't heat up as fast. It doesn't transfer as much heat as the thicker rod.
Because, okay.
Yeah, so when I said, suppose you have a thin rod and it transfers, let's say 1 joule per second, right?
Yeah.
If you put 2 thin rods next to each other, each of them would transfer 1 joule, right, per second? So 2 rods next adjacent to each other would transfer twice as 1 rod. So if I double the area, I double the amount of heat transferred per second.
Okay, but the thin rod would
Heat up faster.
heat up fast.
Yes,
Okay.
because it will have less mass and, yeah, but that's not the
question.
It's
Okay.
about how much heat it transfers in the process. Yeah, not how fast you can heat this. Yeah.
Could you explain how you got a method for dq over dt again?
Oh, it's given.
Oh, it is.
It's a given. So suppose you have a rod, it's length m, length 1 meter, and it's transferring 100 joules per second. And yeah, so all of these were given. It's a given. Yes. Yeah.
On the book, that is piece of C, right? The rate of heat conduction. Or am I thinking?
The power?
Yeah, it just said piece of C is equal to the rate of heat conduction, which is the same as dq/dt, right?
Yeah, I think, I don't remember the exact notation.
Okay, yeah,
That
I
is
just-
book, but I would say, I mean, this is
Just
power,
yeah,
yeah.
okay.
Because power is, yeah,
Oh,
rate
it's
of
in-
energy, yeah. Okay, now radiation, the hotter the object, the more energy it will radiate. And so there is a formula for that. And I will just write it. It's, for now, it's just a formula. Okay, so we will just write it. So if you have conduction, you're going to use this. And I try to motivate why it works the way it does, because, I mean, it's all hand waving, right? The area, probably convincing argument. The temperature, why is it just proportional to the temperature? Maybe to the power 1.5, 1.5, or maybe to the square root of the temperature. But let's just assume everything linear, and then, that's how modeling pretty much works a lot of times. Take the simplest model. If it does the job, then keep it. If it doesn't, then modify it a little bit. Yeah. So, let's go to radiation. So let's say you have an object, and it has a certain temperature.
So, like, when we're making models like that, the reason why we find squares and stuff, do people just do that to make it seem easier to, like, solve for? Cause, like, right now, this is linear, right?
Yeah.
But there's, like, so many other physics formulas
Yeah.
that have, like, squares. Do they
Yeah.
just square stuff so that, like, it makes it easier to
Not always, not always. Yeah.
Okay.
Now, a lot of times, a model is there, like you have a data set and you try to fit it, and then you find, that's a model. Another one is you start from basic principles, from now and, let's say, the laws of thermodynamics, Newton's laws. Those are well-established laws. And then you see where they lead you to, yeah. Just like when we studied friction, we said friction is proportional to the weight, or to the normal force. Is it? Well, macroscopically, to a good approximation. But if you study like brake systems and so on as a mechanical engineer, it's actually not constant. even the coefficient of friction, it varies, and it's a pretty complicated function. Yeah. So you start with the simplest, and then you can add a lot to it. There was a really famous guy. I took a class with him in modeling with mathematical biology, and he always says, if you want a model that includes everything, then you have nothing. So he always says, start with the simplest model that you can get away with, and then you can always add to it stuff, and then to make it more complicated, to make it more detailed. Yeah. But if you want a model that includes everything, then you got nothing, pretty much. You will give up before you start. Okay, so radiation. As you probably can see from my tone, I care more about the processes of heat than these two formulas that I'm going to mention here. I think in the homework we'll probably have two problems of these. One of this one and maybe one of these, if I remember correctly. But you know, they're just formulas. Okay. So radiation, you have dq dt, and by little t here I mean what? What is dt here? Time. Good, because we have capital T. That's the temperature. It is equal to E sigma A and then T to the fourth power. So that's a lot of constants. So, oh yeah, it's a huge power, right?
You have a lot.
Yeah. It actually, this one can be derived from statistical mechanics.
Oh, okay.
Yeah, this one can be derived. Yeah, very few formulas have something to the fourth power, right? I mean, if you just double the temperature, you increase this by what factor? You just double T.
16.
Yeah, 2 to the fourth is 16. Yeah. How often does that happen? So, what are these things? E is just a number. It's called emissivity. It's a number between 0 and 1. So 0 and 1. I think it's inclusive also. Probably. Yeah. Let's see here. Number between 0 and 1. Sigma is a constant called Stefan Boltzmann constant. It's a tiny number. It's a constant. So, by the way, E is usually given to say, just take it to be 1. Usually. Sigma is the Stefan Boltzmann constant. How much is it? It's 5.67 times 10 to the minus 8. And again, you got A is area, and you have to, sigma has to take care of all the units to make them be joules per second. And what is it? It's watts per square meters, and then kelvins to the fourth power. And then A is the surface area of the object. So A is the surface area of the object. So if you're a human, let's say, we have right, we have a surface area. So for a person, let's say, why is it, I mean, when I say A for the object, what does it mean? It's actually the surface area. So in the winter, it's kind of cold, and you don't want to be giving off energy, radiating off energy. What do? Well, the only thing pretty much you can control, well, you can control E by wearing clothes and making them different colors and so on. But the area, you try to shrink your area also, make yourself as small as possible. But in the summer, try to make your surface area as exposed as possible so that you can radiate more, to lose energy in the summer, to cool down. Okay, so that's the surface area of the object. And T is the temperature. And so, kelvins or degrees Celsius? Kelvin.
Kelvin, because it's not.
Yeah, temperature. In K. In kelvins. Yeah.
Is that the heat of the object receiving the heat or the object radiating the heat?
Yeah, this is the heat radiated. And also it can absorb heat.
You know, something that, the temperature for T, is that the temperature of the object
That's the temperature of the
Receiving.
object giving off the heat.
giving up? Okay.
Yes. So if it's both giving off heat and absorbing heat, then you will have, so this is the power radiated, given off. This is the power given off. So how about how much energy are you absorbing? You will put a minus sign, and then E sigma A, and then the temperature of your surroundings. So, for example, so if I want dq dt, the net, how much energy am I giving off? So if it turns out to be negative, it means you're actually absorbing energy. And if it's positive, you're giving off energy. And so the net would be E sigma A, and then your temperature to the fourth power minus the temperature of your surroundings to the fourth power. Now this is the net. We'll do an example in this one. And then, so let's do an example, yeah. So it says here, I think it's a good example. Taking the sun's temperature. What's the temperature of the sun? Based on basically a couple of numbers. The radius of the sun. The sun is radiating, right? So I need to know its surface area. So what's the surface area of the sun if you have its radius? 4 pi r squared. Right? 4 pi r squared. And then I need to know the distance from the sun to the earth, because I know how much energy from the sun we're getting per square meter. It's about 1300 joules per second per square meter. So based on those numbers, you can calculate the temperature of the sun, or estimate. So let me write it down. I'm going to raise this. And so here it is. So the radius of the sun is Rs equals to 6.96 times 10 to the 8th meters, right? The Earth was something constant to the 6th meters, right? And then the distance from the Earth to the Sun distance